In this unit, we would like to find the free spectral range of the imbalanced interferometer. As we will find out, the FSR will depend on the path length difference of the interferometer, as well as an important waveguide parameter, namely the group index. We begin with the optical transfer function for the imbalanced interferometer, where the waveguides are identical and there's a path length difference of delta L. We wish to find the spacing between adjacent peaks, known as the free spectral range, which we define as the wavelength difference between peak m+1 and peak m. We define the argument of the cosine transfer function as delta. The peaks of the interferometer occur when delta is a multiple of 2 pi, namely, where the cosine term is 1 and there is constructive interference. The phase difference between adjacent peaks is a delta m minus delta m+1, which must be equal to 2 pi. Note that the order of the subscripts is reversed since beta decreases as wavelength increases. Typically, there are many peaks in our spectrum, hence we are working at a high order of the interferometer, namely delta is much greater than 2 pi. The propagation constant at each peak is beta m and beta m+1. We can define the difference as delta beta and relate it to 2 pi and delta L. Next, we approximate that beta varies linearly with lambda by defining the slope of beta with respect to lambda. This allows us to relate delta beta to delta lambda. We can combine the above two equations to find an expression for delta lambda. It is in terms of 2 pi, delta L, and the slope of beta versus wavelength. Let's go further since we have an expression for beta equals 2 pi n over wavelength. We perform differentiation of beta with respect to lambda using the chain rule. We can now substitute d beta versus d lambda into our delta lambda equation. This gives us the free spectral range, delta lambda, as a function of wavelength, path length difference, and a function of the waveguide's effective index. The term in the brackets is defined as a quantity called group index. The same expression is found if one considers pulse propagation to find the group velocity. Since we have performed waveguide simulations of the effective index versus wavelength, we can numerically differentiate this data to arrive at the group index versus wavelength. We can also convert the FSR from nanometers to gigahertz. You need to be careful with the units. I find it easiest to convert everything to meters and seconds, which gives me the FSR in hertz. This expression is similar to the free spectral range of a Fabry-Pro cavity. A valid comment to make is that beta isn't really linear with respect to wavelength, particularly since lambda appears in the denominator. Instead, we can write beta as a function of frequency, and beta is much more linear. We will arrive at the same conclusion, however. We define the FSR in terms of the radial frequency. Delta omega equals omega 2 minus omega 1 and is the difference between two adjacent peaks, 1 and 2. In terms of the phase, delta, the spacing between adjacent peaks of the interferometer is the same as before. This time, the linearization we perform is on the effective index n with respect to the frequency omega. We can write that the effective index n is some mean value n naught plus half of the FSR times the slope of n versus omega. We take the phase expression above and isolate n times omega. We can write that 2 pi times c divided by delta L equals n2 omega 2 minus n1 omega 1. Then we perform a substitution of our linearization of n. Finally, we isolate delta omega. Note that we define ng as n plus omega dn d omega. Again, you would get this result if you considered pulse propagation and the group velocity. This expression is in terms of radians per second. We convert this to frequency, and the FSR is C divided by delta L NG. We can convert this to wavelength and find that this expression is the same as we previously found. These are the free spectral range expressions you should use when you analyze your interferometer, whether it is looking at your simulations or your experiments. If you use the NG value from your waveguide simulations, then you should find agreement between the simulated FSR of your interferometer and this expression.